let's get started with the new material. So you remember what we went over last week? What was a big topic?
Sample space.
Sample spaces. Yeah, we were calculating probabilities using sample spaces. And what is a sample space? SP, where S is?
Like an event that occurs kind of thing?
It's the same.
Right, but overall it's just some finite non-empty set.
Oh, yeah.
And P is what?
It's probability.
It's the probability function. So what do we know about P? Tell me the properties we know P has.
Takes S and gives you numbers less than 1.
Less than or equal to 1, greater than or equal to 0.
Right, yeah.
So P is a function from S to the real numbers such that it maps every member of S to some positive real number, and such that if you add up all the right-hand values in P, you get 1. Right?
Mm-hmm.
Okay. So today we're going to start out by talking about an event. An event is just, well, we'll go high level. An event is just a subset of S. So give you intuition for an event. It's the way that Peter was thinking about rolling the dice last time. So when I said when you roll a dice, what are the possible things in S? And I said it's the ordered pairs of what the 2 dice showed. Do you remember that? And Peter thought about it. He says, why don't we just do it what the dice rolled? Like 4. They can roll 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's my possible rules, right? So the way we view it now is we call a particular roll an event. So rolling a 6 is an event. How many ways are there to roll a 6?
1.
5.
If you roll 1 dice, then there's only...
Oh, no, with 2 dice. Sorry. I was always thinking 2 die. Should specify that. We're rolling 2 die. How many ways can I roll a 6?
5.
5 ways, right? I roll 5 into 1, a 4 into 2, a 3 into 3, a 2 into 4, a 1 into 5. 5 ways. So that's what we would call an event. It would be the subset of those ordered pairs. So that's intuition. Let's get the exact definition. So let SP be a sample space, and an event A is a subset of S, and the probability of A, which we represent P of A, is equal to just the sum of the probabilities of the individual elements in A. So what was the probability, if I roll 2 dice, what's the probability of a particular outcome?
136.
136, right? The odds that when I roll those 2 dice, the first one's a 4 and the second one's a 3, is 136. The odds that when I roll those 2 dice I get 1, 1 is 136. So for any particular outcome, the odds is 136. And if there's 5 ways for me to roll a 6, what's the probability that I roll a 6?
536.
536. What did he do? He added up 136 5 times. He did this. He said for each element in A, there were 5 elements in A, take the probability of that event and keep adding it up. Is this too dense, or do you think you got it?
I think I got it.
Dense? Got it? Cool. Alright. So let's look at a concrete example. Probably the one I just said. Probably should have just done the example rather than explaining. Alright. Sample space for rolling 2 die. S is going to be 1, 2, 3, 4, 5, 6 cross 1, 2, 3, 4, 5, 6. How many elements are in S?
6.
6 times
6.
6 for a total of?
36.
There it is. There's 36 elements in here, right? Because this is all the ordered pairs you can make where the first element comes from this set and the second element comes from this set. We have 6 options for the first, 6 options for the second. We have a total of 36 things in there. What's an example of something in S? Something like 3, 4. Right?
Yeah.
So S is all the possible ordered pairs I can make where my first element comes from that, second element comes from that. And what's the probability of getting this exact one, of the first die being a 3 and the second die being a 4? 136. So the probability of any particular roll is 1 over 36, or 1 over the size of S. If each outcome in S is equally likely, then 1 over 36, or 1 over the size of S, is the probability of a particular event. Does that make sense what I said? I might have said a word wrong, I don't know.
Wait,
Got my
say that
words
again.
mixed up.
What?
So, what we're saying is, P of s, of little s, for any little s in there, is always 1 over the size of big S, if everything in big S is equally likely. So we're saying each of these rules are equally likely.
Okay.
So the probability of a particular rule is 1 over however many possible rules there were, 36.
When would it not be equally likely?
If I had a loaded die, or we set the sample space for this, I'm going to toss this in the air, and it's possible that it lands like that, it's possible that it lands like that, and it's possible that it lands on its side. Right?
Mm-hmm.
Those are all the possibilities. Now, it landing like that has a way higher probability than it landing like that, has a way higher probability than it landing like that.
Well, then how would you do that?
I would have all of you grab markers, and I'd have you randomly toss it into the air.
How would you write that?
How would I write that? So we need to come up with labels. So we call this position 1, this position 2, this position 3. So I'd say S is equal to 1, 2, 3. There's no wrong way to do it. And then I'd say P is equal to, well, position 1, that happens 0.99% of the time. Position 2, that happens, oh geez, you're going to make me do tricky math. 0.09% of the time. And then position 3, that happens 0.01% of the time. I did my math right there, right?
Mm-hmm.
Yeah.
That plus that is 1, so 100% of the time it's going to be one of those. So that's the way that we might do it. Anyways, erase those so I don't try and figure them out as we go. Oh, and that's something. And that's something. Okay. Back to what we were talking about. Okay, so this makes sense. Okay, so let's just look at a particular one now. So let's look at the event ruling a 7. You know what it means for a die to rule a 7?
Mhm.
Yeah.
Yeah, the dots add up to 7, right?
Yeah.
So how many ways can we rule a 7? Give me the ways that we can do that.
1, 6,
We can do 1, 6,
2, 5,
2, 5,
3, 4, 4, 3, 9, 2, 6, 1.
wonderful. So there's A. Notice A is a subset of S, right? Every one of these are elements in S cross S. So now what's the probability of A?
1 6.
1, 6.
1/6. What are they doing though? So they're saying since they're all equally likely, it's going to be the size of A times the probability of each of those, or the size of A over the size of S. Because the probability of each particular one was 1 over the size of S.
Okay.
Yeah.
So they got 6 over 36, which is the same thing as 1/6. Anything weird, confusing? Pretty straightforward?
Yeah.
Alright, then let's just continue. Let's look at tossing a coin 5 times. So it's going to come up with some strings of heads and tails. Right? So S is going to be this. How big is S?
2 to the power of 5.
Which is
32.
32. Yes. So now, that's the probability of a particular outcome, right?
Yeah.
Assuming that they're all equally likely, we've got a fair coin. So now let's look at some events. What is the event that I flip exactly 1 heads?
It's going to be 5 over 3.
Yeah, I don't want to write them all out. I just want to know the size of these, so we'll just talk about their sizes. So how many ways can I flip the coin 5 times and have that string of 5 flips only have 1 heads in it?
5.
5, right? Either my first flip is a heads and none of the other ones are, or my second flip is a head and none of the other ones are, etc.
Mm-hmm.
Right? Okay, so what about the probability that I flip 2 heads?
Would that just be 10? Yeah.
25.
10? How'd you get that?
I just, if there's going to be 2, then you just multiply it by the 1 that's what I thought.
How many ways? Give me a good way of thinking about it.
Whoa, isn't, you have,
10's right.
you
I
have
just want a
five,
good way to think about it.
you have five, it's five.
Once I write them out,
What is it?
5 choose 2.
5, choose 2. I got 5 positions. Choose 2 of them to be heads. 5, choose 2. This was 5, choose 1. Now we're doing 5, choose 2. So 5, choose 2, which is 10. But wanted to make sure that you knew how to think about it and had a generic way to think about it. Because if I would have said, what about if I had 4 heads and 20 flips? Then you know it's just 20 choose 4, right?
Yeah.
So I want you to have a generic way to think about it rather than relying on the simple example. Okay, so now what's the probability then of A?
5 over 32.
5 over 32. And what's the probability of B?
10 over 32.
For
5, choose 2.
5 sixteenths. You were just plugging in. Okay, any questions on that example? Pretty straightforward? Seems risky. Okay, so let's move on to the next one. Now we're looking at rolling a die 10 times. So what does S look like? We're going to do S is the order pair, is the 10 tuple. Why did I only do 6?
Because it's 6 cross 6 10 times, right?
Yeah, 6 cross 6 10 times.
So you
Not
have 6.
10 cross
And
10
then you
6
have-
times. So, oops.
So you have 10 spaces.
Wait, what?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So S then is going to be the set of all the 10 tuples we can make with the numbers 1 through 6, right?
Yeah.
I have 6 options for the first roll, 6 options for the second roll, 6 options for the third roll, 6 options for the 10 roll. And if you were to see the number here, 1, 3, 3, 2, 6, 1, 4, 4, 5, 6, you know that meant on the first roll I got a 1, on the second roll I got a 3, on the 10th roll I rolled a 6. So this is one particular outcome in here. Now S has lots of things in there, that's just an example of one thing in there. How many things does S have in it?
6 to the power of 10.
No.
So the size of S is equal to what?
Isn't it 6 to the power of 10?
6 to the power of 10?
Yeah.
No one has a different answer? You gonna make me give it to you? Good job. No backtracking. I like that. Okay. So that's the size of S, 6 to the 10. Now, let's say we want the event A is not rolling a 1. What's the size of A?
5 to the power of 10.
That was some quick math. Alright, so 5 to the power of 10 is the event not rolling at A. What's the event
Yeah.
not rolling a 1? So if we were to do the event now, rolling a 1, rolling at least 1, 1, for B, then what's the size of B equal to?
At least 1, 1.
Yeah,
Put in there.
6 to the power of 10 minus 5 to the power of 10.
wonderful. 6 to the 10 minus 5 to the 10.
Isn't that just 1 to the power of 10?
Not by a mile. Here's how you can do a sanity check. Look at 2 to the 10 minus 1 to the 10. You got 1024. Oops, 1024 minus 1.
Oh.
So, drastically different numbers. Anyways. So this is the probability of, or not the probability, but this is the event not rolling a 1. And now you know how to calculate their individual probabilities, right? Let's write that down here real quick.
Yeah.
Yeah.
What's the probability of A now equal to?
5 to the power of 10 over 6 to the power of 10.
Yeah.
So that's 5, 6 to 10. And what's the probability of b equal to?
It'd be
6.
five.
6 to the power of 10 minus 5 to the power of 10 over 6 to the power of 10.
Or wouldn't that just be 5 to the power of 10?
No.
The
What
same
about,
way that 2 to the power of 10 minus 1 to the power of 10 divided by 2 to the power of 10 is not 1 to the power of 10. Although in this case it's actually pretty close. But that's a coincidence.
wouldn't it just be like what?
It's exactly what Emma said.
Oh,
So we'll write that out and then see if you can see why I was waiting to see if someone would say it differently.
I mean, you could do like 1 minus the probability of A, I guess.
Yeah, well, that's a good way to do it. That's where I was ultimately trying to get, but I thought you'd say minus 5, 6 to the power of 10. If the probability of not rolling a 1 is PA, then the probability of not rolling a 1, which is the same thing as rolling at least 1, is 1 minus that probability, right?
that makes sense.
If there's a 60% chance that I won't roll a 1 in 10 rolls, then there's a 40% chance that I will roll at least 1 in 10 rolls. Does that make sense? Because going back and forth like this, thinking about it this way is very useful. Have we talked about set complement in this class?
Set complement.
The complement of a set.
I think
Sounds
we did.
familiar.
Sounds familiar.
Do you know what this symbol means? A with a line above it.
Sure.
Not topologically
Yeah, I was
speaking.
gonna say
We're
topology.
not talking about the closure of a set. We're talking about the complement. In topology, we wrote it this way.
Yeah,
Yeah.
That
What's the complement of A?
one
everything not in
universe
A.
that's in
It's a set of everything that's not in A,
Yeah.
right? So, probability of B was the same thing as the probability of A not.
oh,
Does that make sense what I'm saying? A was the event rolled a 1. So A is a collection of all the 10 tuples that have a 1 somewhere in there. Oh wait, which one was it? Not rolling 1, sorry. A is the event we didn't roll a 1. So A is a collection of all the 10 tuples that do not have any 1s in them. Right? A complement then is the set of all the 10 tuples that do have a 1 in them. Does that make sense? It's all the 10 tuples that aren't in A. What are the 10 tuples not in A? They're the ones that have a 1 in them. So A complement is that. So you'll notice that the probability of A complement is 1 minus the probability of A. You see that before I erase it?
yep.
Alright. Just want to point that out. We'll come back to that idea, but this seemed like a natural place to put it there because I accidentally did that. Because I just put that in as an example now. Let's see. 4 of a kind in poker. Do you know what 4 of a kind is?
Yeah,
Give me an example of a hand that's 4 of a kind.
all the aces.
So he has all the aces and then 1 extra card. Poker hand, you have 5 cards. 4 of a kind means 4 of your cards are the same card by rank, not by suit. You know the difference between suit and rank? Okay, so that's what 4 of a kind is in poker. So, we know that S is equal to, we're going to make S equal to all poker hands. We're not actually hurting anyone's hands. So, then the size of S is equal to what?
How many cards are there in the deck again?
52.
52.
Okay, so it's 52 times 51 times 50 times 49.
We went over last time why that thinking almost works, but not quite. You ultimately have to divide by that 5 factorial.
Yeah.
So isn't it like 52 choose 4?
So close.
52 choose 5.
52 choose 5. You got a deck of 52 cards. You choose 5 of them. That's your hand. I don't know why you choose 4.
Oh, I see you have 4 of a guy.
Oh, sorry. S is a set of all poker hands.
Okay.
Right? Okay. So now we want A is the event. A is going to be our event. You have 4 of a kind. So now I want the size of A. How many possible hands are there where you have 4 of a kind? How many ways can we do that?
12, 13.
There's 13 ways to choose which 4 of a kind you're going to have. So you're really close. Now just finish it.
It's, it's like
13 choose
times,
4.
5 choose 4. I don't know.
No, because once you choose which rink, once you choose your rink, that determines 4 of your cards. Right? So we're looking at a particular hand. 1, 2, 3, 4, 5. Particular hand is going to be a set of 5 cards. There's 13 ways that you can choose which rink you're going to have. But now there's only one way to pick the other cards. So how many ways can I finish off the hand now?
12.
You're close to the right idea. I don't just have to pick a rink, I also have to pick a suit.
Is
12 times 4. 12 choose 4.
12 times 4, or 48, right? There's 48 cards remaining. It doesn't matter which card I choose after that,
Oh.
right?
What? No, I'm lost.
Poker hand that has 4 of a kind. There's 13 ways I can choose the rank that you're going to have 4 of a kind of.
Yeah.
So now I give you those 4 cards. There's 13 ways I can give you those 4 cards. After I give you those 4 cards, how many cards do I have left?
You have 48.
And now you randomly pick one.
Yeah.
So 13 ways to pick your suit, or pick your rank, and then 48 ways to finish off the hand. That make sense?
Yeah.
So, the size of A is 13 times 48. Yeah. Does that still not making sense?
Yeah, it's kind of not making sense.
It's kind of not making sense. Let's look at a particular example.
Okay.
So we'll start out with I take all the aces.
Okay.
So I now have all the aces. So I have ace of suit 1, ace of suit 2, ace of suit 3, and ace of suit 4. Right? How many cards are there left for me to choose from?
48.
48. Okay. Now instead of all the aces, I have all the 2s.
Okay.
I have all the 2s. How many ways are there to finish my hand?
48.
48. Now I have all the 3s. How many ways are there to finish my hand?
48.
How many times are we going to do this process?
13 times.
13 times, and for each of those 13 times, there are 48 options on how to finish.
Yeah.
13 times
But wouldn't
48.
it be like 13 choose 4 times 48?
No,
Why?
because it's not 13 choose 4 is I have 13 cards, you randomly choose 4. That's not what's happening.
Oh.
Once you choose one, once you choose the rank, the other 3 cards have to be the other 3 cards with the same rank. You have no choice about it.
Mm-hmm.
So once the rank is established, 3 of your cards are completely determined. And all that remains to establish is the last card.
Okay.
So you choose your rank, that determines 3 more cards. Now you pick randomly one of the remaining 48 cards. There's a possible hand.
How does that take care of like how many different ways you can arrange the hand?
We don't care about order.
Why
A
not?
poker hand, order doesn't matter. So it's sets. All poker hands, a poker hand is a set, not a list. So a poker hand
Oh,
would be
okay.
these in a set.
That makes more sense. Then yeah, that makes.
Because, yeah, in poker, it doesn't matter what order you're holding your cards in, your hand is your hand. Make sense?
Yeah.
Okay. So that was a poker hand. Let's go on to another one. Here's a fun one. A couple has 4 children. Is it more likely that they have 3 of the same gender and 1 the opposite gender, or that they have 2 of the same gender? 50-50.
It's the same
It's
like.
not right.
It's not.
Or is it the same likely?
It's the same one.
So the chance that they
No,
have,
it's not.
no, the chance that they have 3 of the same and 1 of the opposite is 1/4. And then, the chance of 2 of each is 4 choose 2 over 16.
It's not the same likely because X and Y.
Well, don't you have 50%
It's-
chance?
It's 75% and 25%.
Alright. So we'll do, first off, let's talk about S. What's the size of S?
16.
16.
Why is it 16?
You have 4 children. There's 16 ways you can have them by gender. You have 2 options for the first child, boy or girl. 2 options for the second child, boy or girl. 2 options for the third, 2 options for the fourth. 2 times 2 times 2 times 2 is, that was quick math. Make sense?
Yes.
Okay, so now we'll say that A is, which one did I say first?
3 of the same gender, 1 of the opposite.
Yeah, so let's do B first. So B is 2 of each gender. How many ways can I do that?
4 choose 2.
4 choose 2. I have 4 gender positions to fill. I need to choose 2 of them to be a particular gender. Then the other 2 are automatically not that gender.
Right.
Right?
Okay.
So, 4 choose 2, that was for B. This is equal to 4 choose 2. And what is 4 choose 2? Those numbers too big?
I just forgot how to do it.
You don't remember the formula?
No.
So first off, intuition. What is 4 choose 2? It is all the 2-element subsets you could make from a 4-element set. That's what it is by definition. Right? Now the equation we associate with that is 4 factorial over 4 minus 2 factorial times 2 factorial. Okay, now let's see if you can do it. 6. Are you guys okay? What's going on? This is 2 factorial, this is 2 factorial. I mean, even if you don't want to try canceling top and bottom, you should be able to calculate this in your head. What's 4 times 3 times 2 times 1?
24.
24. What's 2 times 2?
4.
What's 24 divided by 4? Okay. It's not that hard, even if you're like having a hard time canceling. Just, they're small numbers, right? Okay. So we got that one done. I dare not ask. What's the size of A?
4.
4? How'd you get that?
It's 4 choose 1.
4 choose 1, right? So which one's more likely?
B.
B. If we aren't too careful about our thinking, you can look at, I can have 4 and choose 1 to be a boy, plus 4 and choose 3 to be a boy. Those are all the ways that I can have one of one gender and 3 of the other gender. So here's a case where I have 1 boy and 3 girls. Here's a case where I have 3 boys and 1 girl. Make sense?
Mm-hmm.
So now this is equal to 4 choose 1 is easy, but 4 choose 3, that's a head scratcher.
Okay, but then it's 4 choose 1 already.
It's the same thing, that's a big old A. 4 choose 3 and 4 choose 1, same thing. Choose has that symmetry. Because if I choose 3 elements, I choose 1 element to leave behind.
Oh, yeah.
Yeah.
I remember.
There we go. Memory. It's a wonderful thing when it works. Do we have any questions about that?
Yes, I do.
Okay.
I'm confused why you'd have to add that, because 4 choose 1, isn't it if it's a boy, then all the rest are girls, and if it's a girl, then all the rest are boys?
4 choose 1.
So are they the same thing?
You just have to think about the problem some way. If I say, how many ways can I have just 1 boy? 4 choose 1.
Yeah.
How many ways can I have 3 boys? 4 choose 3.
Okay, but then
So how many ways can I have 1 boy or 3 boys? The sum of those.
Okay.
I don't know, keep asking stuff if it's still weird somehow.
It's still weird.
Okay, what's weird
Because
about it?
then what if you just do a girl? Because then you figured out your boy problem. Because
Well,
you have the possibility of the boy.
If we think about this as choosing boys, 4 choose 3 boys is the same thing as 4 choose 1 girls. If I choose 3 of them to be a boy, I chose 1 of them to be a girl. And if I choose 1 of them to be a boy, I choose 3 of them to be a girl.
Yeah.
So whether you think about, I'm going to choose my boys, making the rest girls, or I'm going to choose my girls, making the rest boys, it's the exact same. And you get identical numbers.
So then why don't you do the same thing on the bottom?
On the bottom,
Yeah.
so I can think about the problem 2 different ways. I have 4 kids and I can choose 2 of them to be boys, making the other 2 girls, that's this. Or I can think about it as, I've got 4 children, I'm going to choose 2 of them to be girls, making the other 2 boys, that's this. I can't count the same configuration twice.
That's what you're doing on the top.
No, these are 2 different configurations. When I do 4 choose 1, these are counting ordered pairs that only have 1 boy and have 3 girls. All the ordered pairs that have 1 B and 3 Gs are counted by this. All the ones that have 3 Bs and 1 G are counted by this. This counts all the ones that have 2 Bs and 2 Gs. I can't count all the ones that have 2 Bs and 2 Gs and then count all the ones that have 2 Bs and 2 Gs again. That's duplicate counting. Up here, we didn't never count the same quadruple twice. Does it still feel fuzzy? Because if it still feels fuzzy, this is worth just writing now to make it extremely explicit. Because it's not that big of a set, right? So let's look at our set. Our set is we could have girl, 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 boy, girl, girl, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, boy, girl, boy, boy, girl, girl, boy, boy, boy. Is that 8? Good, got them all. And then down here, repeat, but make the first one a B instead of a G. Okay. So here they all are. And now let's just actually count them and see how each of these count them. So 4 choose 1. I'm saying this is all the ways where we have 1 boy. If we want to think about the choose in terms of boy. We'll think about everything in terms of boys. So 4 choose 1. That's all the ones with 1 boy. So let's see. That's 1, 2, 3, 4. 4 of them have 1 boy. This is all the ones that have 3 boys. Let's see. That's 2, 3, 3, 3, 3. Notice that I've counted all the ones that have 3 of one gender and 1 of a different gender, for a total of 8. Now when we look at 4 choose 2, that's this one, this one, this one, and this one.
No. You missed 2.
Up. That one, and that one. Thank you. So those are all the ones that have exactly 2 of each.
Okay.
So it's completely clear. Everyone's good? That's a lot nodding. Okay. So I'm all good. Okay. So, and we see that this one's more likely. Which, if you were to go ask a random person on the street, they most likely say this one. Another one of those ones where your intuition is typically wrong. Right?
So wait, 8 is more likely?
it's more likely that you will have 3 kids with one gender and 1 of the other than you'll have 2 of each.
Interesting.
That's weird.
It is weird. Because, well, kind of.
I thought
It's weird if you don't think about it too much, but you think about it enough. It's like this right level of, at first it's like, yeah, but then you think about it and you're like, no, it's kind of weird. Then you think about it more and you're like, no, that makes sense. Okay. So we're good here. On to our proofs. Right?
Yeah.
Okay, we're still on this. Do not let me go to this whiteboard without moving the camera. I did that in Halloween. Very unhappy about it. Okay. So let A and B be events in the sample space SP. What do we know about A and B so far?
They're events in sample spaces.
There's
Yeah, so they're subsets of S. Wonderful. Okay, so now I'm going to prove that the probability of A plus the probability of B is equal to the probability of A union B plus the probability of A intersect B. Now what does that formula look a lot like? The conductor? Tell me what to write.
Circles.
A, the
Size.
size. The size of A plus the size of B is equal to the size of A union B plus the size of A intersect B.
Wonderful.
Didn't we prove this on the midterm?
We already proved this. I don't know if we did on the midterm. You might just use it for a problem. Because you do accounting for this, so I doubt it. Anyways, so we already have this. Now look at this, and it might just jump out to you as obvious that this is true, given this.
Yeah.
But we're going to prove it. Here's the way that we're going to prove it. Now, keep in mind what these things are. When I say the probability of A, what is that? That is this sum. That's the sum of all the little a and big A, summing up their probabilities. So this just represents a sum of terms, this just represents a sum of terms, this just represents a sum of terms, this just represents a sum of terms. Right? What I'm going to show is that for any particular term, it shows up on both sides of the equations the same amount of times. So you're summing up the exact same numbers on both sides, therefore they're equal. Make sense?
Okay.
Yeah, it's pretty straightforward. So let little s be some element of big S. And observe that there are 4 cases. Either S is in A and S is in B. Or S is in A, or S is not in A and S is in B. Or we have S is in A and S is not in B. Or S is in neither of them. These are all the possible cases, right?
Yeah.
Okay, now we're just going to show in each case that S shows up on both sides of the equation the same number of times. I'm just saying observe that it does, but I'll point out to you as we go, because I just didn't want to have to write a bunch. So, observe that PS shows up in each side of the equation twice in case 1. So in case 1, when S is in both of them, then we get a PS here, and we get a PS here, and we get a PS here, and we get a PS here. So you get 2 on this side, 2 on this side, it shows up the same number of times on each side of the equation.
Gotcha.
Make sense? Everyone good with case 1? Alright, case 2. So in case 2, that's this case, then it's going to show up on each side of the equation once. PS doesn't show up here, P of S doesn't show up here, P of S does show up here once. P of S does show up here once, and it does not show up here.
Right.
So it shows up on each side once.
Right.
Case 3 is identical, but now we switch which one is in. So now it does show up here, not here, and it does show up here, not here. It shows up on each side once. Finally, case 4, P of S doesn't show up because it's not in any of those probabilities. So we just barely showed that for any little s and big S you choose, the term associated with it shows up on both sides of the equation the same number of times. So they're adding up the exact same numbers, so they're equal. Make sense?
Yep.
Yeah.
Pretty simple proof. Therefore, blah, blah, blah. They're the same. So now you have that formula which hopefully appeals to your intuition. Next, bunch of properties. So looking at this formula up here, what would happen if A intersect B is the empty set? What's the probability of the empty set?
0.
0, right? So, if this is 0, then the probability of A plus the probability of B equals the probability of A union B. So if A intersect B is the empty set, then this plus this is equal to just this, because that's 0, right? So that's what my first statement here is. Sorry, where am I? Right here. If A intersect B is the empty set, then the equation just looks like that. Pretty straightforward?
Yeah.
Okay, next, 2. Notice that the equation, flipping the order I write the terms in, the probability of A union B plus the probability of A intersect B is equal to the probability of A plus the probability of B, right? That's just flipping the order I write the terms, right? So then, if I remove this term from this equation, I could have only made this side of the equation smaller. I couldn't have made it bigger. I either made it the same, or I made it smaller if I get rid of that term, right? So that term is 0 or some positive number. So if I get rid of that term, then that turns the equals into a less than or equals. So this is always the case, in other words. P of A union B is always less than or equal to P of A plus P of B. Straightforward? Wonderful. What's the probability of all of S? 1. How did you know that?
I just took a guess.
You just took a guess based off of the board? By definition, a probability function has to add up all its terms to 1. So this is a probability on all of S. Sorry, this is a big S, not a little s. This is on the entire big set S. So when we sum up the probability of everything in S, we better get 1. That's by definition of a probability function. What's the probability of the empty set? You can read. What's the probability of the complement of A? 1 minus the probability of A. That's what we went over with the stuff I erased. But you remember this, right?
Yeah.
A complement, that's everything not in A. So the probability of A not happening is 1 minus the probability of A happening. If there's a 60% chance of A happening, then there's 1 minus 60%. What's 1 minus 60%?
40%.
40%. There's a 40% chance of A not happening. You do it with 1 and 100% are the same thing. So if I say you got 1 on your test, you're happy?
Yeah.
As long as I don't give a divisor. Okay. So, any of these weird? Any of these you want to see examples for, or are you ready to just continue? Ready to continue. She's spoken. Alright. So, 4 people are chosen at random. What are the odds that 2 of them have the same birthday? Or better yet, let's just play around with people in here for a second. When's your birthday?
October 17th.
When's yours?
March 14th,
When's yours?
September 23rd,
If someone says your birthday, raise your hand, by the way. When's yours?
February 18th.
When's yours?
February 28th.
When's yours?
July 20th.
And mine's November 10th. None of us have the same birthday. What were the odds of that?
Not very likely.
the odds of none of us having the same birthday?
Yeah, what are the odds that none of us have the same birthday?
Pretty much.
You think that's got to be pretty normal, right?
Yeah.
You do know how to calculate those odds?
Yeah, just take a while.
It'll just take a while. Tell me the general. Are we still on this one?
Can you read
Oh, that's other
Yeah.
stuff. I'm like, why do I already have? Get rid of all our boys and girls.
Let's do that.
Alright. So, how would I calculate the probability of none of us having the same birthday?
You would calculate the probability of all of us having the same birthday, and then minus that from 1.
Well, how many ways can we have? First off, how many different ways can we all have our birthdays?
360.
Ignoring leap years. Sorry if any of you are born on a weird day. So 365 to the, how many of us are there? Are you a leap year birthday?
She almost was.
Oh.
But she was born on a leap year.
Oh.
There's 7 of us.
So there's 7 of us. So this is how many different ways we could possibly have our birthdays, right?
Yeah. Yeah.
I guess.
Okay? And then how many ways so now we've got to fill out our birthdays. 1, 2, 3, 5, 6, 7. So we're going to say A is the event that we don't have the same birthday. So the size of A is equal to, how many ways can we have Peter's birthday?
365.
365. How many ways can we have Emma's birthday if it's not the same as Peter's?
364.
364. And then Laura is, and then Rhoda is,
362.
and Lee is,
361,
and Stafford is,
360,
and I am,
359.
which is pretty intuitive.
Yeah.
Right? So then the probability of that happening, the probability of A is equal to just the size of A over the size of S, right?
Yeah.
These are all the ones where we don't have the same birthday. These are all the ones, and this is all the possible birthdays, right? So now, obviously, is that number big or small?
No.
Big.
It's really close to 1%, right?
It's close to 1%.
Or close to 1. Sorry. This is really, really close to 1, right? We took 265 over 365 times 364 over 365 times that over 365 times that over 365. We basically did 1 times 1 times 1 times 1 times 1 times 1 times 1 7 times, which is basically 1, right? There's a very high chance that we don't all have the same, that we don't have a birthday in common, right?
Yeah.
Yeah.
There's 365 days out there, and we've only used up 7 of them. Right? We had a lot of days to spare in making sure that we don't have the same birthdays.
But, yeah. Right.
But yeah,
Yeah.
Sure,
But-
sure, it's a high number.
Okay.
yeah, you can
Well,
calculate this. We need to pull out the old calculator. Get Betsy out here.
That's a high number,
You'll be able
but
to
S
write that
is
up.
way bigger than that.
Well, we're going to look at, I'm going to calculate the probability of A. I'm looking at this number divided by this number.
Oh.
So when I do that division, that's the exact same thing as writing each of these over 365 and multiplying them.
But what about the 7?
Okay.
Right? That's how I can write, that's not the size of A anymore. This is the size of A over the size of S. S is 365 times 7 times. A is 365 times 7 times. So my probability is that ratio. And that ratio is basically 1 times 1 times 1 times 1 times 1 over and over again, right?
It's
Well, no, 'cause it's
No.
smaller.
Yeah.
It gets smaller, but 359 over 365 is still a number close to 1, right?
Okay.
So 365 times 364 times 363 times 362 times 361 times 360 times 359 divided by 365 to the power of 7 is equal to 0.94376. What did I say? 94376?
Yeah.
So we'll say 94.376% is the odds that we do not have a birthday in common. Right?
Okay.
So then I just picked a random number. What if 23 people were in this room? What do you think the percent should be close to?
The same.
No.
Give me a number roughly.
89.
So we got 89%. Anyone else pulled out there? Somebody go crazy like 5%?
More like 85.
We got 85 coming up.
That would be higher.
Rhoda wants to go up.
Like,
This is the probability that no one has a birthday in common,
With 7 people.
right? So with more people, the probability that no one has a birthday in
I'm
common
not
should go
saying higher
down.
than 4.
Oh, you're just saying higher than what I wrote. Anyone else got a wild guess?
Why are we guessing? Like, why don't we just calculate?
Just to appeal to your intuition, I already have the calculation.
What is it?
Because that was one that we had ahead of time, so I could do it.
23 people.
Alright.
Just trying to help your intuition. No one else is going to guess, only 2 people. It's roughly 50%.
What?
That's as close as you can get to the cutoff.
Wow.
Seriously? What the heck?
Yeah. So this is a common trick for people on the stage putting on a show or whatever. If you got a row of like 30 people there, then you say, I'm sensing that someone on this row, 2 people on this row have the same birthday, right? And then you have them go down the aisle saying when their birthday is, and the odds are that 2 of them have the same birthday gets pretty high. Should we calculate it for 30 people?
Yeah.
All right,
That seems weird.
let's see.
Yeah, that seems messed up.
Because, like, not a lot of people in the school have.
So if we do 30, we're going to count all the way down to, what number am I going to end at if I count 30 of them?
335.
Almost.
334? 4 or 6?
4 or 6. That's almost 335. When we counted 7, we went to 359. So when I count 30, I'm going to go to?
336.
Wonderful. 336 is going to be my last number.
Yeah.
All right, so 365, don't let me go past it. Let me put parentheses. 365 times 364 times 363 times 362 times 361 times 360 times 359 times 358 times 357 times 356 times 355 times 354 times 353 times 352 times 351 times 350 times 349 times 348 times 347 times 346 times 345 times 344 times 343 times 342 times 341 times 340 times 339 times 338 times 337 actually only hit 6 times 336. Stop. Divided by 365 to the power of 30, which is 29%. So once you have 30 people, then there's 29% chance that they don't have a birthday in common. So that means that there's a 71% chance that they do have a birthday in common. So if you're in a class with 30 people, chances are 2 people in that class have a birthday in common.
But, like, we
There's a 71% chance that 2 people have a birthday in common. Right?
That's weird.
Of course, that's not really a random select. Would that? I think it's still that, yeah. Assuming that's a random selection of people. Should be.
It's interesting.
Yeah, pretty cool.
What is 100%? Like, how many people do you have to have 100%?
To get to 0%, infinite. Because it's always something. Right? The answer is no. You'd have to have 366 people to get 0%. Right? Because once all the days are used, the most people you can put in one room all together such that none of them have a birthday in common is 365, unless you count leap years, and 366. But we don't count leap years. Okay. So that's called the birthday problem. Common problem has its own name. Now we'll move to the other board. Take out the charger. All the way over Rhoda's head. Not sure we can lift it that high. Snug it up against her. Just a little more. Okay. So that was section whatever. That was the next section. Here's the section after that. That was events. This one is on conditional probability and independent probability. So conditional probability means, what's the probability given some condition? To help you with your intuition really quick, what's the probability that a typical student is late for school? Probably not that high, right? Am I overestimating you?
Yeah.
The probability that a student's late for school, not very high. The probability that a student's alarm clock doesn't go off, not very high. The probability that a student is late for school, given that their alarm clock doesn't go off, that's a whole other story, right?
Okay.
So there's some intuition for the types of things we're going to be talking about given conditional probability. And you see how it drastically changes our probabilities. So let's look at an event real quick. So A, this is rolling 2 dice. So talking about rolling 2 dice, A is we rolled an even, B is we rolled an 8. With me?
Yeah.
So what are the odds of A? What's the probability I roll an even?
It's just 1 dice, right? You're saying
2 dice.
2 dice.
2 6-sided die, because rolling an 8 needs to be possible. So we've got 2 die, I roll 2 die. What's the probability that my roll comes out even?
16. Not 16.
Isn't it just like
Yeah.
1%?
Is it not 16? 15,
No, it's
30?
18.
18
Yeah.
out of how many?
36.
Yeah, so we'll try to run that down in our heads.
Yeah.
I don't know how you were counting it.
I just was thinking half. I was thinking exactly what
Okay. Oh, you were just trying to do that the hard way.
you did. Yes.
I see. Okay, 1/2, right?
Yeah.
Half our rolls are going to be even, half our rolls are going to be odd.
Yeah.
Yeah.
Pretty straightforward. Don't need to write that one out. What's the probability that we roll an 8?
8 out of 36.
Well,
How many different ways can we roll an 8? 7 minus 2.
7 minus
Why are you saying
5.
5 ways we can roll an 8. That's the quick math. 5 out of 36 is our probability then.
okay.
We can roll a 6 and a 2, a 5 and a 3, a 4 and a 4, a 3 and a 5, a 2 and a 6. Dice probabilities are really nice to work with, by the way. Because you have 2, 3, 4, I probably already went over this with you.
Isn't there more than 5?
These are all the possible outcomes with the die, right?
Mm-hmm.
How many ways can you get a 2?
1.
1. How many ways can you get a 3? 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. So you can just count up. So all I do is memorize that we start with 1, we end with 1, and 6 goes to 7. So there's a 1/6 chance for a 7. 7 is obviously the most likely, right? Everyone who's ever played dice knows that.
Yeah.
So you keep track of the most likely one and the ends, and it's just real easy to count from there. So probabilities with 2 dice is really easy to do in your head. For all you gamblers. For all of you. Right? No? You don't gamble? You do? All the time? That's all the money you lost? Don't show the camera. Okay. We're over here. So there's 5 out of 36 ways that you can possibly roll an 8.
Mm-hmm.
Okay? Now, what's the probability that you roll an 8 given that you rolled an even?
536.
Rolled an 8, given that you rolled an even.
Yeah, so I roll my 2 dice, and I say, okay, it's even, but you can't see what they are. What's the probability that I rolled an 8?
Oh. 4th. No.
Not sure how you're doing that.
1/2.
How many of my rolls are even?
1 out.
Half of them are even. So 18 of my rolls are even. How many of my odd rolls can possibly produce an 8?
0.
0. So all my rolls that produce an 8 were even rolls, right? So there's 16 even rolls. How many of them are an 8?
5.
5 of them.
So
Out of 18,
5.
not 16.
Oh, did I say 16?
Yeah.
Sorry. You're right, I meant 18. So 5/18,
Oh.
right?
That makes sense.
Yeah.
These are all my even rules. These are how many of them are 8. These are all my rules. These are how many of them are 8. Now this one, let's see if you can figure out. What's the probability that I rolled an even given that I rolled an 8? 100%, 1. So notice that those two are very different questions with very different answers. Right? I rolled an 8. What do you think the odds are I rolled an even? 100%. Okay. So now I think we're ready for our definition of conditional probability. That was an example to establish your intuition. And this is exactly what you were doing, but let's go over it. Let A and B be events in SP such that the probability of B is not 0. Then the conditional probability of A given B, the probability of A given B, is represented this way. It's the probability of A and B divided by the probability of B. That's the probability of A given B. Now, notice what you did up here. This is B given A. So you said, what's the probability? Well, it's not quite what you did, but you'll see how it's the same thing. Let's re-ask this question thinking about it this way. What's the probability that I roll an even and it's an 8?
Well, your probability is 5.
No. So don't think about what we already did. Pay attention to the question. What is the probability that I roll an 8 and that I roll an even?
Isn't it just when you roll 8?
536.
536. Wonderful. It's just 536. Right? That's the probability that I roll a 5 and I rolled an even.
8 and
Oh, what did I say?
so 5.
Good. Keep calling me on that. That's the probability that I rolled an 8 and an even.
Just 8 is even.
8 is even, so it didn't change it.
Yeah.
Rolling a 5, rolling an 8, and rolling an 8 and an even doesn't change anything. So in other words, A and A intersect, or B and B intersect A are the same thing. B is equal to B intersect A is another way of saying that. So the probability of B and the probability of B intersect A are the same. B is, I rolled an 8. A is, I rolled an even. Take all my even rolls and intersect it with all my 8 rolls, and I'm left with all my 8 rolls.
Okay.
Yeah.
So the probability of B intersect A is the same thing as the probability of B is 536 in this case. Now, what's the probability of A? What's the probability of an even? 1/2. Or 18 over 36.
Which is just 5.
And so that's just equal to the 36 go out top and bottom. That's how it's always going to be when you do these problems. We're typically going to be. So that's just 5/18, which is exactly what we said before. That's using the formula.
Oh, right.
So you just switch it? So you do? If they switch?
Yeah, I just had one called A and one called B, but that doesn't matter. Just plug them in according to this. Whichever one comes first, put here. Whichever one comes second, put here and here, and you're fine. Okay, so now let's try and establish intuition for this. Here's S. S is all this space. And we're going to pretend that each outcome in S is equally likely. So that means that the probability of A is just the area of A divided by the area of S, right? If I say that we'll call the area of S 1, pick my unit so the area of S is 1, and I tell you that the area of A is 0.3, then the probability of A is 30%, right? So let's pretend that A are these events and B are these events. And so then the probability of A occurring, given that B occurred, is this area divided by all of the area in B. You see that?
Area and B?
Yeah.
Yeah.
So it's going to be this area divided by the area of B. What are the odds of this happening, of A happening, given that B happened? That's just that intersectional area.
Okay.
Do you see that? Is that intuitively making sense? So that's the intuition for this equation. The probability of A given B is the probability of A and B occurring divided by the probability of B occurring. It's the probability of this intersection divided by the entire area of B, looking at it from that picture. That's just trying to establish intuition. We good? I'm appealing to your intuition?
Yeah.
Okay. So now let's go back to our spinner and ask some questions about it. First off, what's the probability of spinning a 1 on that spinner?
50%.
50%. I say more like 49.7, but okay.
You got it.
So now, question, what's the probability, well, we'll ask another question just to make sure it makes sense. What's the probability of doing an odd, how do I say odd without it looking like a 0? We'll just write it out. What's the probability of an odd equal to? I spin an odd number.
5 8s.
5 8s. Everyone agree with that?
Yeah.
Here's 4 8s, here's 1 8. Together we got 5 8s. Okay, so now my question is, what is the probability of spinning a 1 given that I spun an odd?
And then just work this.
1 given it.
This is not 100%. Wait, no.
What?
That's not.
Oh, wait. Yeah, it's 4 fifths.
It's 4/5. How'd you do that?
Because 1 plus 3 equals 5. If you look at it, it equals 5. And then 1 is 4 of the 5.
Wait, what?
1 plus 3 equals 5.
The 1 plus the 3 equals 5.
I see what she's saying. She's saying this has 4 8s, this has 1 8, so together they account for 5 8s. So this is 4 out of the 5 8s. Right?
4 fifths. I got that.
4 8s, or sorry,
So
Well,
she got 4 out of 5.
yeah, 4 out of 5. Because, so she's saying, what's the probability of spinning a 1? Sorry. What's the probability of spinning a 1 intersected with the probability of spinning an odd? What's the probability of spinning a 1 and an odd? Well, that's the same thing as just spinning a 1, right?
Yeah.
So in this case, it's 1/2. Or if she, think about the way that she was thinking about it, she's saying it's 4 8s divided by the probability of just an odd. And what's the probability of spinning an odd?
5 8.
5 8s. And now cancel out your 8s and you're left with 4 5ths.
Yeah.
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 Make sense?
Yeah.
Think so.
Appealing to the intuition? Feel like you can set up a sample space for that?
Yeah.
Yeah, sample space is real easy. That's easier than all these questions. You just make a set with 1, 2, 3, and 4 in it, and then you make a probability function that assigns 50% to 1, 25% to 2, 12.5% to 3, 12.5% to 4. If you want to be useful, right?
Mhm.
Okay, let's move on to the next one. When a coin is flipped 5 times, what is the odds that the first flip, how
What
do I
is it
have
tails given there are exactly 3 heads?
Oh, that's just my team on this. That was messing with me for a second. Okay. I kept reading that as first plus flip. Alright. What is the odds that the first flip was a T, tails, given that there are exactly 3 heads? The odds that my first flip is a tails is always just 50%. Doesn't matter what you know about anything, right?
Yeah.
So it doesn't matter. There should just be 50%. So this is going to introduce us to independent events.
When
So knowing about the rest of my coin flips in no way helps you know what the first flip was, right?
Yes.
No. I'm just getting you guys to say the wrong thing. But wonderful. That I broke your intuition. So now let's go over the problem.
Hey, wait a minute.
It's not 50%.
Okay.
Alright, so let's look at this one now that I got you to think about it wrong. what is the probability that the first flip is a tails, given that there are exactly 3 heads? Okay? So,
Given their
we'll
exact.
do
There's only 4
A
times,
is
bro.
first tails. There's 5 flips total.
Yeah, but that's only 4.
And B
Oh.
is exactly 3 heads inside the flips. Or exactly 2 tails, however you want to think about that. So, let's look at, for our formula, we're going to need A intersect B. Well, let's look at the size of A real quick. What's the size of A? How many flips start with the tails? Half of them. So the size of A in this case is 16.
Okay.
Twice. Yeah.
Oh, sorry. The size of S is what? The size of our entire set of outcomes is 32.
Because 2 to the power of 5.
I have 2 options for the first flip, 2 options for the second, 2 for the third, 2 for the fourth, 2 for the fifth. 2 times 2 times 2 times 2 times
Yeah.
32. I can't say 2 times 2 times 2 as fast as I can say the entire alphabet. Did you know I can say the entire alphabet in a quarter of a second?
You
Sorry.
can.
It's a family guy joke.
No.
I didn't.
Peter Griffin says you're just jealous because I can recite the entire alphabet in a quarter of a second. Duh.
And you said what?
Duh. He just screams nonsense really quick. There. The entire alphabet in a quarter of a second. Duh.
You should at
It's a
least start
joke.
with like
No, because the Z at the end makes that more prominent. Because it's the last one you say. Don't be mean. Alright. Anyways, back to math. Okay, so the size, the number of possible outcomes we have if we flip the coin 5 times is 32, right? Half of those start with the tails.
Yes.
How many of them have exactly 3 heads?
5 choose 3.
5 choose 3. Holy cow, we didn't have to
Wow.
struggle with that forever. What is 5 choose 3?
5.
Okay, so it's
1.
Don't think 5 choose 2, that's too fast.
It's 1.
5
Or it's
factorial over 5 minus 2 factorial times 3.
Oh, I forgot, bro.
Fine.
120.
24 times 5.
Oh, okay, nice.
How do you do that?
Well, 24 is composed of a 2
6,
and a
so
4, and I want to multiply by 5, right? 5 times 2 is
No,
10.
10. 5 times 4 is 20.
it's 10.
120.
You're fast.
It's 10.
10. Did you do 5 choose 2? No?
Yeah,
No.
we did 5 choose 2 and 5 choose 3 at the same time.
Yeah.
Something.
Wait, what?
Yeah, it's 5 choose 2.
Yeah, don't we have 5 choose 2 written up here somewhere?
I think we did.
Whatever, let's just keep going.
We don't have 5 choose 2 written anywhere.
Yeah, we don't. Let's just keep going.
So we haven't already solved this and figured out that it is 10. Okay, so now what do we need? We need the size of A intersect B, which is the hardest part of figuring out these problems. Right?
A intersect B.
So this is how many have exactly 3 heads, right? Another way to think about that is this is how many have exactly 2 tails.
Yeah.
Now, how many have exactly 2 tails where the first one is a tails? So if I require, here's how you think about this. If I require my first one to be a tails, how many ways can I finish it with only one more tails to use?
4.
And how did you do that? What's the generic way
4
to
choose
solve
1.
that? 4 choose 1, wonderful. So 4 choose 1. Or in this case, it happens to be 4. But if I give you different numbers, then you can figure out how to do it, right?
Yeah.
If I said it was a string of 100, and I said that the first one's a tails, and you have 17 tails to plug in there, then it'd be 99 to 17,
Yeah.
right? So there we go. So 4, that's the size of this. So now we're ready to do, what is the probability of A given B? That's equal to the probability of A intersect B
Over.
divided by the probability of B. Which is equal to, what's the probability of A intersect B?
Over.
No, it's probability now. This is the size of A intersect B. There's 4 of those. 4 over 32, or
1 over 8.
1 over.
maybe we'll leave it as 4 over 32 actually, because then it will cancel out with whatever this is. What's the probability of B?
10 over 32.
10 over 32.
So it's 4
Oh, it actually
So it's
makes
equal
sense.
to 2/5. So
Yeah.
that only happens 40% of the time. So if I tell you, I flip a coin 5 times and I have my string of flips here, or I flip 5 pennies down in an order and I don't let you see them, and I tell you that there's 3 heads in there, what's the odds that it starts with the tails? That my first flip was tails. It's only 40%. It's not 50% anymore.
Wait a second.
Wait.
Wait a second.
How?
So we have some random string
Probability is so weird.
of 5 characters, right?
Mm-hmm.
And I tell you, and you know that all those characters are just H and T, and I randomly assign H's and T's. Now I cover up the string, and I tell you 3 of them are a heads. What's the odds that the first one is a heads?
Isn't that the first one?
Yeah, the first
Yeah, I know, but now I'm just asking a different question that I think will help you think about it. So I have a string of H's and T's. I tell you that there's 3 H's, which means there's how many T's?
2.
2 T's. Okay, what's the odds that my first letter is an H?
60.
60! So the odds that the first one is a T is,
40.
which is what we calculated here.
Why is it 60?
He finally made the intuitive leap.
I'm so confused.
It's 1 minus 4.
I have a collection of letters here,
Because there's one.
and all you know about it is that there's 3 H's and 2 T's, right?
Yeah.
And they're in some random order. What are the odds that the first letter is an H? I have 5 letters to choose from. How many of them are an H?
3.
3.
So
3
3/5, which is
60.
60.
Actually makes sense.
So that's the intuitive way to do it. Here's the way that we solved it. But you see how information about the flips tells you what the first flip is. Here's how you can help your intuition that it should help you. What if I told you that, okay, all my flips were H's, what's the odds that my first flip was a tails?
0.
You see how knowing information about the flips helps?
Yeah.
Mm-hmm.
So then if I say 4 of my flips were H's, what's the probability that my first flip was a tails? 20%. Only one of the 5 is a tails. So if I have to randomly choose one to be the first one. Okay, so think we're flipping into your intuition? All right. Now let's try this one. See if you're finally gotten it. We flip a coin 5 times. What are the odds that the first flip was a heads, given that the last flip was a heads? Question, is it going to be more or less than 50%? And if you say it's going to be 50%, I might get a little mad.
Wait 1 second.
It's less than 50.
1 second.
Yeah.
What is the probability? So I flip a coin 5 times. What's the probability that the first one was a heads, given that my last one was a heads? Is it more or less than 50%?
Less.
Less. That doesn't make sense.
It's more, isn't it?
It's more,
Because you have
isn't it?
4 this.
Wait.
No, you don't.
Coin.
I don't know. I'm confused.
That's good. Stretch your intuition. Anyone got a definitive answer on what it should be?
Give me like 10 minutes.
And any reason why that makes sense? I'll let you think about it. That's fine. There's no rules to this game. Except no hitting the teacher. Seems like a safe one. But have at each other. Anyone feel confident about anything?
Nope.
Have I just broken you?
Just about.
Well, we're going to stare at this until someone has something to say.
I'm like halfway.
Alright. He's halfway through his math. The more you tip your head, the more the knowledge stays in, right?
Yeah. Try to keep it in.
You guys really just stumped?
Yep.
You can't figure out this probability. Talk about just flipping a coin a couple times. You need some help?
No.
No? Alright.
Would it be more because of the stuff we did over there?
It seems safe. Since you know one of them is a heads, it seems like more, and stuff over there, we're bound to have covered the material to answer this.
I'm 100% sure I'm not right.
That's
Oh, what's your answer?
50%.
It's 50% and you're 100% sure that's wrong?
Yeah.
Maybe he's just tricky.
Maybe. Maybe it is 50%. What's wrong with that? You only know one of them is a heads. And that's not very many. So it still has to be 50-50, right?
I know too.
Alright, so here's my hint on how to help you think about it. The coin is flipped 5 times. What are the odds that the last flip is a heads, given that the first flip is a heads? Does that help?
No.
Yes, so much.
No? Oh, so she's got it. Should we reduce this down to 2 flips?
Yeah, we did.
Okay, we flip a coin twice. What is the probability that my second flip is a heads, given that my first flip was a heads?
Wait, it doesn't matter.
100%.
I flip a coin, it comes up heads.
Yeah.
Now I flip a coin and I cover it up. But you knew my first flip was a heads, so that helps. So what was my second flip?
That.
50%.
Did the fact that you knew my first flip help in any way?
No.
No! So it's still just 50-50.
Wait. So
So-
I did do it right.
When you were 100% sure, you were wrong.
Well, I went and did all that
I
math
am
in my head, and I was like, I got 50%.
So the answer is still just 1/2. Knowing that the last flip was a heads in no way helps you predict what the first flip was.
But knowing that there are 3 heads.
We can calculate this if you want. Yes, because here's the difference in the intuition there. When we knew
There are exactly 3 heads.
that there are exactly 3 heads, we didn't know anything about their position. That could have still been the first one that was a heads.
That means the other 2 are telling.
Here we knew that the last one was a heads. That in no way helps us predict what the first one was. If I knew that one of them was a heads, that changes things. If I know the last one's a heads, that in no way helps me predict the first one. You see what I'm saying? You see how those are 2 different scenarios?
Yeah.
But now let's actually calculate this out and see that it's the exact same. And we'll do it the long way. Okay, So a coin is flipped 5 times. We'll call A is the first. The first is heads. B is the last is heads. Right? Okay. So what's the probability of A? 1/2, 50%. What's the probability of B? 1/2. What's the probability of A intersect B?
1/4.
Yeah.
1/4. 1/4 of my coin flips are going to start with the heads and end with the heads. 1/4 start with the heads and end with the heads. 1/4 start with the heads and end with the tails. 1/4 start with the tails and ends with the head. 1/4 start with the tails and end with the tails. Make sense? So we don't need to write all of them out. Okay, so now the probability of A given B, or B given A, doesn't matter which order we do this in, is going to be the probability of A intersect B over the probability of B, which is equal to 1/2. 1/4 divided by 1/2. Wait, 1/2 of a fourth is an 8. See if that confuses anyone.
No.
If I divide a fourth into halves, I end up with an 8, right? So a fourth divided by 1/2 is an 8.
No.
Or is a fourth divided by a half? How do you divide a fourth by half and get a half? Am I confusing you guys?
Stop talking.
1/4 divided by 1/2 is the same thing
No,
as
it's 1/4 divided by 2/4.
1/4 times
4/2.
2 over 1, which is equal to 1/2. Right?
Yes,
Okay.
that's how we do math.
It's actually a common IQ test problem. It's something to that effect.
Oh, really?
Yeah.
I failed it.
They have you calculate what's a fourth divided into a half. Anyways, I can't remember exactly how the question's worded, but it's worded to make you want to multiply them together instead of dividing. Anyway, we calculate this and it comes out 1/2. Okay. Let's see. So that covers this part. Okay. So now we're ready for independent events. What do we mean when two events are independent? Intuitively, what we mean is information about the first, no way it helps me predict the second. Two coin flips are completely independent. If I know that my first flip was a heads or tails, that in no way helps me predict whether or not my second flip was a heads or tails. Those are completely independent events. That's what we mean by independent. Here's mathematically what we mean by independent. Let A and B be events in this sample space, then A and B are independent if and only if the probability of getting both of them is equal to the probability of getting the first times the probability of getting the second. So intuitively, let's say I flip a coin twice. A is the probability I get a heads on the first flip. B is the probability that I get a heads on the second flip. Those are completely independent events intuitively, right?
Mm-hmm.
So what's the probability that I get a heads on the first flip and a heads on the second flip? That's the same thing as the probability that I get a heads on the first flip times the probability that I get a heads on the second flip. Make sense?
Okay.
And logically equivalent ways of writing this formula are that the probability of B given A is equal to B, and the probability of A given B is equal to A. If you give me information about B, it in no way changes the probability of A. If you give me information about A, it in no way changes the probability of B. And how can you see that this equation is the same as this equation is the same as this equation? That's looking at this. You see it?
Yeah, I think I see.
Right? Because if the probability of, if this is the same as the probability of A, move that over, you get that. And then if we were to switch the B's with the A's, then you get the other one, which is the same as the top one. So However, it helps you think about independent events in your mind. Pick whichever one appeals to your intuition the best and stick with that interpretation. Whether it's this way or this way, doesn't matter. Okay, another definition. Kind of a mouthful, but it's a simple idea. So let me go over the idea first, and then the mouthful will be kind of obvious. So, it's very tedious. If I already create a sample space for talking about rolling one die, it's really annoying to have to create another sample space for talking about rolling two dice, and another sample space for talking about rolling three dice, etc. Make sense? So, if I already have a sample space like S equal to 1, 2, 3, 4, 5, 6, and I already have a probability function, which in this case we'll just say P of S is equal to 1, 6, then rather than constructing a new sample space from scratch when I want to perform this event twice, roll two dice, perform the event twice, notice that rolling two dice and rolling one die twice are identical, right? There's no difference between rolling two dice and rolling one die twice. So, if I want to continue using events in this thing over and over again, rather than having to come up with new sample spaces, we're just going to construct a sample space from this one. So given this sample space, SP, I'm going to construct a new sample space, S to the end, and we'll use the same P that you already gave us. But the difference is now, how do I calculate the P of a particular event in S? So, let me do concrete to the side here. So let's say, concrete example to the side. Now I want to create a sample space where we roll the dice twice. How would I do that? I would do S crossed with itself. Shorthand for that is S squared, right? And I'd give it a new probability function where the probability of a particular roll, I'll use square brackets on the outside to distinguish from my ordered pair. The probability of a particular roll, like 1, 6, is equal to the probability of 1 times the probability of 6. The probability of one of my rolls being a 1 times the probability of one of my rolls being a 6.
So 136.
So in this case, 136. So that's how I redefine my probabilities.
Okay.
So notice that I'm just referencing this function now twice to calculate the probability of an event. So this is what we're going to call, I can't remember exactly what it is. Well, we'll go over that here in a second, but let me show one more. So imagine that we did this 3 now. 3 times. That's the same as rolling 3 dice, right? And so now a particular outcome from this might be something like 1, 6, 2. And the probability of that is just going to be the probability of 1 times the probability of 6 times the probability of 2, etc. Okay, so now let's go over the definition. I think you'll get it. So let SP be a sample space that we already have that we're working with. This would be like the simple one that we have here. Let S to the n denote the set of length n lists of elements of S. So when S was 3, or when n was 3, then S sub 3, what does this represent? All the 3 tuples with elements from S.
Okay.
S of n denote the set of length n lists, or n tuples is the way I typically say that, of elements of S. You with me on that? Still confused? No? Okay. So then we have a new sample space, kind of. Not quite a sample space because this P is the same as that P. So then SNP is the n-fold repeated trial sample space. It's where we repeat it n times. Right? Like rolling a die 3 times here. So this is the n-fold repeated trial sample space where the probability of a particular outcome is equal to the product of the outcomes of the individual elements in the n tuple. It's exactly what we did over here. Any confusion there? I know it's kind of a mouthful, but the idea is actually pretty straightforward. It's what we intuitively were doing when we were thinking about rolling the dice twice. Right? Okay. Give an example, I guess. So let SP be the sample space for a single die. So we'll say it's this exact thing that we have written right here. There's SP. And let's consider doing it twice. What's the probability then of 1, 1? 136. And 136. Okay, so yeah, that was easy for you to make the leap. You understood that's something we've been doing the whole time. There was nothing hard about that. Right?
Okay.
Wonderful. Okay, last thing we need to talk about is tossing an unfair die.
Coin.
Coin, thank you, because there's only two outcomes. We're just using an unfair coin, but this is true for any binary event. Binary meaning there's only two options.
Okay.
A coin flip is a typical one where there's only two options, but it could be anything where there's only two options. So this is an analysis of binary events in general. We'll use an unfair coin as our example. So let's say that the probability of heads is equal to P. Or a little row I'll do, just keep our difference. If it's equal to rho, then what's the probability of tails equal to?
Wait, what is
One
Yeah.
minus
1 minus P.
1 minus P. Should we do little p instead of rho? Little p for the probability of heads instead of rho. Rho is just a Greek letter.
Thinking like row.
I thought he like named the little row. That's kind of cute.
Okay. So now, let's consider the probability of something like a heads, 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 tails, heads. What's the probability of this thing?
E to the fourth times 1 minus p.
P to the fourth times 1 minus p. You see how she did that?
No.
Well, you have HP times and then 4 times.
So we can represent this probability this way, right? And what's P of H?
P.
Little p. So we have little p times little p times little p times little p. So we have 4 of those.
Yeah.
Times, what's the probability of tails?
1 minus P.
1 minus p.
Okay.
Smart.
And that's true regardless of the order that these come in, right? So if I also did tails, heads, 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 then that would also be equal to p to the 4 times 1 minus p.
Yeah.
Okay.
Okay? And are we going to get into binomials? No? Not safe for next week?
Fun.
Are we talking about random variables first? Okay. Well, guess we won't get into that anymore yet. So that's all it is. So that's the end of the material. The last thing that the author does is an in-depth analysis of the Monty Hall problem. How many of you have heard of the Monty Hall problem? One of you. All right. The Monty Hall problem, here's the way that the game worked. The host of the game had 3 doors. And behind 2 of the doors is a goat. And behind 1 of the doors is a car or something like that. So here's the way that the game worked. You would choose a door. Leah, pick a door. 2. So Leah would pick this door. We'll put a dot above it to say that's the door she's currently choosing. Then me, as the game show host, Monty Hall, I would open a door that the car is not behind. So I'd open one of these doors. The car can only be behind one of these 3 doors, right? So for sure, once Leah picked one, there's going to be one of these doors that still has a goat behind it, right?
Yes.
How do we know that?
There can't be a car behind both these doors. There's a car only behind 1 door, and then the goat's behind 2 doors.
Well,
Right?
what if the car's behind number 2?
Doesn't matter. The point is, one of these doors for sure has a goat behind it, right?
Yes.
Yeah.
So I, as a game show host, randomly pick one that I know has a goat behind it, and I say, Leah, there's a goat behind this door. Question. would you like to stick with number 2? Or would you like to switch to number 3? Or does it even matter?
It does matter.
How do you know?
You stick with 2.
You stick with 2. How'd you know?
I watched a video on YouTube.
Why do you stick with 2?
Go watch it again.
Why do you stick with 2?
You don't, you switch. The answer is you switch.
Why?
But most people would stick with 2, thinking that he's trying to bait them into switching.
Why do you switch?
Why do you switch? Here's the intuitive way to switch, or to see it. To make this appeal to your intuition, I think the easiest way is to just play the game over and over again. Here's how we're going to play the game. I always switch, you always have to stay the same. Okay? Now, Emma's going to write down a list of a bunch of random numbers, 1 through 3. Just completely random, don't let Rhoda see it. And we're going to keep score between Donnie and Rhoda. You always have to stick with your option. I always switch. We're going to see who wins more. You have your list? Okay, so she's got her list. Rhoda, choose a door.
3.
Rhoda chooses 3. Did she get it?
Yeah.
It was 3. Rhoda wins. Because Rhoda chose number 3. Emma tells us, okay, it's not number 2, so now I'm stuck with number 1. Or Emma told us it's not number 1, so I'm stuck with number 2. But either way, Rhoda got the card. Right?
Okay.
Okay, let's play again. Rhoda, pick a door.
2.
2. Emma, was it behind 2?
Yeah.
Alright. Rhoda's killing me. Alright. Rhoda, pick a door.
2.
2. Emma, was she right?
No.
No. So tell me a door that it's not behind. So Emma would open one of these doors now. Which one would you open?
1.
So Emma would open door number 1. So now we know there's a goat behind there. Rhoda sticks with number 2. I switch to 3. So now I would have won. Rhoda loses in that case. You see it?
Yeah.
Okay, so I win in that case. All right, next. Rhoda, pick a door.
1.
1. Was she right?
Yeah.
Rhoda's killing
I
it.
think I'm winning.
You are winning. We just gotta keep playing long enough, though.
Yeah. Okay.
All right, Rhoda, pick a door.
3.
3.
Yeah, she got it.
What'd you order?
She's too in sync with you.
Okay.
Rhoda, pick a door.
3.
3.
No, she didn't get it.
So now I would have won, right?
Yeah.
No.
Okay, so you picked 3. Emma, tell me a door that's not behind.
1.
Oh,
1, so I picked 2.
Oh my.
Did I win?
Yeah.
Oh, crazy. That's
But
skills.
but you wouldn't know if it was 3 or not.
No, I just have to do what you didn't do. If it was 3, you win. If it wasn't 3, I win. Right?
Yeah.
Okay, but wait. There's only one person playing the game, right?
Right, there's only one person playing the game, but we're going into alternate universes. Right? So it's like you and I are playing simultaneously,
But listen.
and the only difference is you're always going to stay, I'm always going to change.
But if you were playing the game show host, why would you always switch if you could still be right?
I could have been wrong. I could have lost that round. It turned out I won, but I could have lost.
So why would you keep switching? Like, why not just stay?
You'll see it eventually. And I'm guessing that most people have already seen that. What are the odds that Rhoda wins?
33%.
1/3.
Yeah.
You're going to win 1/3 of the time. I'm going to win 2/3 of the time.
No, you're not.
Okay, let's keep playing. Pick a random, or Rhoda, pick a door.
2.
So Rhoda picks 2, and let's pretend Donnie picks 2. Now, Emma, tell me a door that it's not.
3.
It's not 3. I switch to 1. You stay at 2.
Okay.
Who wins?
You.
I win.
But what if it was still 2? I could have won just as easily as you could.
You could have won,
And you.
but you didn't, and I won.
But I'm still winning more than you are.
You still are, but that's going to change. Rhoda, pick a door.
3.
3. Was it 3, Emma?
No.
So I win.
No.
Okay, let's go through it. You picked 3, and I picked 3.
Oh wait, you do win. Okay, but only because you know. if I wasn't telling you if I was.
You didn't tell me anything. Look, let's play again.
Okay, go on.
Rhoda, pick a door.
Oh, 1.
Rhoda picks 1. Emma, tell me a door that it's not.
3.
3. So me and you both chose 1, right? Emma says it's not 3, so now I'm saying, okay, then it's 2. Who wins?
It could still be 1.
You do.
It could have been, but I won, because it was 2.
But how do you know that?
Every time you don't guess it right, I win. Every time you do guess it right, you win, right?
Yeah, but you don't know that in the game show.
How don't we know that?
Because there's only one person playing.
Rhoda, do the minus thing, minus the 1 minus the thing. You have 1/3 chance of guessing.
So what are the odds that I win if I win every time you don't? 2/3. So if you switch, you have a 2/3 chance of winning. If you stay, you only have a 1/3 chance of winning. We can keep playing until it just appeals
Well,
to
I
you.
just don't get it. Will you just explain it to me?
Look, you can't ever change, right?
Yeah.
So right out the start, you only have a 1/3 chance of getting it.
Yes.
If you don't get it, I get it. The only difference between me and you is I always switch, you always stay. So if you always stay, you have a 1/3 chance.
Oh, okay.
If you don't always stay, then you have a not 1/3 chance. You have a 1 minus 1/3 chance, which is a
2/3.
2/3 chance.
Okay. That's weird.
Yeah, we can quit while I'm ahead.
Probably best.
Well, the gap between us is just going to get bigger as time goes on.
I was doing a really good start there.
You were doing really good. So that's the wonderful thing about the law of large numbers. Your little luck at the beginning means absolutely nothing in the big picture. That's why Vegas always wins. If enough people gamble, doesn't matter if a few of you are getting lucky, doesn't matter if you're lucky at the beginning, if you keep gambling long enough, Vegas wins.
That's why we don't gamble, boys.
I'm sorry.
Okay, but yeah, if you want to see the sample space set up for the Monty Hall problem, you can read through how the author goes over it. I think the intuition is enough rather than seeing it completely set up. So we'll call it there. Make sure I have all your homework.